perfect. Okay, so hi, I'm Yannay, and if you want to follow my slides on your laptop, you can use this link. I hope you copied it, or just take a quick photo and then you can write it, and we can start. So yeah, I used an interesting framework called Reveal.js, so you can just follow it, and it's in Markdown, so you can also read it afterwards on GitHub and do whatever you want with it. And these are the slides. So welcome to my talk, as was very nicely introduced. Who I am. I'm Yannay. I'm a security researcher, independent security researcher. I'm Israeli and Swiss to some extent, and I love climbing. So if you know a nice gym after the talk or in the evening, I would be happy to go. Why we are here, and that's all the French I know or don't know. I'm gonna show a comprehensive overview of all many working exploits against GLibC Malloc as they work today, and it should serve as an introduction or reference. And everything here is going to be, you're going to see lots of links to other articles and other papers, and also some of my work, some of other people's work. And obviously I cannot go over all the details, but I'll try to explain as much as I can. So today's agenda, giving these objectives, and I can leave the mouse away. Okay, so we're going to see an overview of the heap implementation. It's going to be a very brief overview. Then we'll see how we can leak pointers to bypass ASLR to disclose memory addresses. We'll then continue with having a controlled write of data to memory addresses we shouldn't have access to, but we're exploiters, so we get this access. And we'll finish with code execution, how to hijack the flow. And as a bonus, I'll show my CTF setup. This is my hidden agenda. I want to see tomorrow's challenges in the 2 days in the CTF, and if there is a heap exploitation challenge, I would be very happy if this presentation would serve as a reference to solve the challenge. So, internals. This is a brief version of GLibC Malloc internals. It's a very, very good explanation of how the heap works internally. And, oops, what did I do? Okay. So, yeah, so we have first the API. And you know, there is the Malloc API call. A user needs a place to store some data, so they request memory from the system. They're doing it with the Malloc API call. The user just says, hey, system, I need memory of this size, and the system grants him a region, a chunk of memory with at least the size, the requested size. And the user gets a pointer to this memory, and he can write there and do whatever he wants with it. Free is the opposite. It's the analogous or opposite operation. The user frees the memory it received from the system before, it deallocates the memory, and the system claims it back. And there is also realloc, in which the user needs a different size of memory, but retaining the old data. So it requests the system to increase or decrease the size of memory that was allocated. And the system do it in place, or maybe move it to another place while retaining the data that is already there. There are a few other API calls. It's not a comprehensive list. You can read the fine manuals. Then to help to implement all this functionality, internally there are some structs used. And we start with the chunk, which is a logical structure. It's not exactly how it is in the C code, but this is what you would see in memory. Chunk is the basic memory unit used by the system to allocate and deallocate memory. And chunks can be in two possible states. They can be either allocated to a user or freed. When they're allocated, basically a chunk looks like this. You have the size, the header, and then you have the user data. The user receives a pointer to the user data. So the user writes their data, users write their data in the user data area, and right before the pointer to the user, you'll see size. When the chunk is freed, what you would see is something like that. You have the size, then you have pointers, because chunks are in linked lists, so you have forward and backward pointer, and sometimes they're in more than one list, so we have the next size and previous size, and in the end of the chunk you have the size again. So the size is written twice, once in the beginning of the chunk and once in the end of the chunk. Oops. Woo. So chunks, it's in 64-bit system, the minimum size is 20 hexabytes, so it's 32 bytes, and the granularity is 10. So basically, the free least significant bits are free to use as flags, and the least significant bit is used as the previous in-use chunk, which means that the chunk adjacent but previous to this chunk is not, if this bit is 0, the previous chunk is not in use. So it's freed and it can be used by the system for other users. And really big chunks are mapped, and it's not in the scope of this presentation, but there is a different mechanism to handle really big chunks. So I said that the chunk is a logical structure. Really, in the C code, you would see this struct, the malloc chunk struct, which is quite similar, but not exactly. It starts with the previous size, as the size of the previous chunk, and then follows the size of the chunk, the forward, backward pointers, and so forth. You can see it's not aligned with a chunk, but it's almost the same. Here on top, you can see the malloc chunk struct, which has the previous size and size, and in the bottom, you can see the chunk, what we logically call a chunk. And you see that the previous size, this field is only valid if the previous in-use bit is off. So if the previous in-use bit is off, you can read the prev size field and know the size of the previous chunk. And it means that the size of the previous chunk, the size in the end of the chunk, coincides with this field of previous size. So this is how it works. When you free a chunk, what you see, the system writes the size of this chunk in the end of the chunk, which is basically assigning the previous size field of the next chunk, and it turns off the previous in-use bit. So this previous size field is valid, and you can read it. So if you want to know the size of the previous chunk, first you check the least significant bit in the size field. If it's off, you can read the previous size field and see the previous size, the previous chunk's size. Okay, that was a lot. Next thing, we have bins. Bins are just linked lists. All chunks, when they are freed, they reside in some linked list. And there are 4 kinds of linked lists. They're called bins. First, there are the fast bins, which is a singly linked list. It serves as some sort of cache. There is a different list for each size. So for the size 20, you have the 20 bin. Then for size 30, you have the 30 bin, so on. And these chunks are always considered in use, so they're not merged with other chunks. It's a kind of a hack. Then you have the unsorted bin. Unsorted bin contains all the chunks before sorting. So when freeing a chunk, you toss it into the unsorted bin, and it waits for sorting. It's doubly linked circular list. Then we have the small and large bins. Small bins are also for each size between 20 and 400 hexa. There is a different bin, so we have a small bin of 20, small bin of 30, so on and so forth. Yes, there is some overlap. Sometimes chunks of small sizes would be in the fast bins, and sometimes they will be in the small bins. It depends on the algorithm and how you move chunks around between bins. And then you have the large bins, which has range of sizes for each bin. So you have, for example, the range of 400 to 430. That would be a bin on its own, and it's a sorted list. So you can iterate it, and if you free chunk of size 400, it will be inserted into this bin. Then you free another chunk of size 420, it will be inserted in this bin, but after the 400. So it's always kept sorted. Okay, this is a new data structure that was introduced in GLibC 2.26. I think it was released last August. And it's called Tcache. It's the thread local storage caching mechanism. And it's basically an array of singly linked lists of chunks. It's very similar to the fast bin. However, it can serve all sizes. So again, there is a list for each size, but it's not limited by sizes. It's limited by the number of chunks it contains. So there can be a single linked list for the size 300, and then there could be a single linked list for the size 40. It depends on how it on the chunks you're freeing. It's a huge performance enhancement because you keep the memory locality for the threads, you keep it in the same CPU, in the same thread, so on. But they didn't even try be secured. So if you read the implementation of the malloc, you'll see there are many integrity checks, or at least a few integrity checks about the data structures being used. And when they implemented Tcache, they didn't really put any integrity check in there. So they weren't even trying. You can see it's quite of a patch, but it's a huge performance enhancement. The last data structure is the arena. The arena is just the heap descriptor itself. You can see here there is a bins and other heap info. You can see the fast bins, then you can see the other bins, the unsorted small and large bins. And you also can see a mutex for serializing accesses to the data structures. And there is also the top, which is interesting. Top is a pointer to the wilderness. The heap starts in with no chunks in it. The heap mapping itself, before it's fragmented into chunks, it starts as wilderness, just this whole memory of empty memory, wilderness, waiting to be splitted into chunks. And the top points to this area, to the point that was not splitted yet, that is still waiting to be fragmented into chunks. There are also secondary arenas. It's a list of arenas, but it's not in my scope today. And that's about it. So this is the summary. You can see, this is from GLibC Malloc internals. You can see the arena, and you have the single linked list of fast bins, the doubly linked list, the circular doubly linked list of bins. That's more or less what you have. In terms of algorithms, they're quite simple. So the free works by just tossing the chunk you're freeing into the fast bin or into the unsorted bin, depends on its size. And quite quick. Alloc is a bit more complicated, but what you're doing, you're looking for exact fit bins. If you don't find it, you start to merge it, coalesce it, throw it around, sort it, put it in the right bin, then you're looking again for exact fit, and if you cannot find exact fit, you're looking for best fit. If you don't find best fit, something that can serve the allocation request, you're splitting the top, you're splitting the wilderness. Okay, so that was the internals very briefly. If you really want to know more, you can read the code or GLibC Malloc internals. I really recommend it. Moving on to how to leak information. As exploiters, we want to leak information. Why do we leak pointers? You want to see memory addresses. Why do you want to do this? We want to bypass ASLR, right? You don't know where in memory the program is loaded, so that's one of our objectives. We want to write reliable exploits. Even if we do know, it's important to verify ourselves, and also to know which version of libc we're exploiting. Sometimes you can just access the victim software, leak some pointers, and then figure out, oh, it's libc version 224. Great. So what can be leaked in terms of pointers? Well, pointers to the heap, of course. Chunks are in the heap mapping area, and they point to each other. So if you leak these pointers, you know where the heap is located, and also pointers to GLibC. Because the main arena, the heap infrastructure, this resides, at least the main arena, resides in GLibC data section. So if you leak a pointer to this struct, you basically know where the GLibC location is, and you can even know which version of libc you are using, because this struct is in different offsets in different versions. Okay, so how do you do it? So the first way is to read the use after free, and in this presentation, I assume you have some sort of heap vulnerability in your hand, so it's either use after free or heap-based buffer overflow. And if you can read the use after free, basically what you do, you free, the idea is that free chunks contain pointers, and user data coincides with this forward pointer. So one of the pointers in the heap actually coincides with the data you're reading, which is nice. So if you can read free chunks, you're basically leaking pointers. If you read free chunks that are in the fast bin or in the Tcache, you're reading pointers to the heap, as we said. And if you're reading chunks that are in the unsorted or in the normal bins, you either read pointers to the main arena, to the GLibC data section, or you're reading to the next chunk in the heap. So you can also leak in the heap in this way. And let's see an example. So this is my amazing animation. And so we start with an empty heap. Everything is wilderness, and the top points there. And you can see the unsorted bin is a circular list. It's actually double linked, but I only wrote just one side of it. And you see it's empty. And now we start with allocations. So we allocation P0, which is of size 100. And you can see the least significant bit is on, signifying that the previous chunk is in use, because in the start of the heap, actually there is nothing before that, so it's technically in use. And then we allocate another chunk. We don't assign it to any variable, but it serves as a separator. So when we free P0, it will not merge with what's coming next. We're making another allocation, let's call it P1 of size 120. Right after that, you can see the wilderness is moving. Again, the least significant bit is on. And then we make another allocation of a separator. So when we free P1, it will not merge with the wilderness. It will not merge with the chunk before it, because they're both in use. And then we're freeing P0. So when freeing P0, basically we put it in the unsorted bin. This is in GLibC 224. Most examples would be on GLibC 224, unless I say otherwise. So in this case, you free P0 and it goes into the unsorted bin. You can see a circular linked list where the FD points to P0 and P0 points back to the unsorted bin. Then we free P1 and we also insert this one to the unsorted bin. So we have our list just grew. We have the unsorted bin pointing to P1 because it points backward. It's a FIFO, so it's first in, first out. Then it points back to P0, which points to the head of the list, which is the unsorted bin in the main arena. And now we are reading it as the exploiter, so we can actually read what P0 is pointing to. And P0, what's written in P0, it points to the unsorted bin, so it's a GLibC pointer, and the libc pointer, and then P1 points back to the heap, so we're reading a pointer to the heap. And this is how you leak pointers. Another way is to use overlapping chunk. This is a different method. The basics is that you can allocate some readable data, and you have a chunk right before that data that you can overflow into. So you overflow into this chunk and change its size, enlarge its size synthetically, and then you make an allocation which split the chunk you just overflowed. So when you're splitting this chunk, you take this chunk back and the system splits the chunk. So splitting the chunk, it overwrites the pointers right after the split, which coincides with the data you can read. And then you read these pointers and you get the leak that you're looking for. There are two examples here if you want to see the real details how it was used. They're a little bit different, so I recommend reading both of them, and I'll talk about these examples later also. Sometimes you don't need a leak, so this is also to cover that aspect. So you can do partial overrides, like usually, like you can sometimes do in other cases that you don't have a leak and you want to bypass ASLR. You can chunks are pointing to each other, assuming you want to, for example, override something in the libc section. You can just do free two chunks. One of them partially override it to point to the other would point to glibc. You can also partial override the second one, and you get something pointing to glibc, which you can sometimes write via that pointer. Maybe you need more bits, so you do some brute force. It works. And there are two examples here. One is both of them from the Mockless challenge from 2017. One is mine, one is Stefan's, I think. You're in the crowd? I have no idea. You should be here somewhere. So both are interesting, and I recommend reading them. Another way to bypass ASLR is with relative right. So there is a trick that a really big mapped chunk is allocated adjacent to the to glibc for some reason. It's some optimization of the kernel. So if you have a relative right to this mapping, you basically can overwrite some do partial override to pointers in the glibc, and you just bypassed ASLR. This is an example for it. Technically, they did have a leak in this example, but I think it can be done also without a leak, and it demonstrates the fact that big chunks are mapped and they are adjacent to the glibc mapping. So after we've leaked some pointers, we know where things are. It's time to do some attacks and write user control data. So I have 3 categories in my head for attacks. These are categories that just help me think about it. You won't see them anywhere. And the first category is structural attacks, which are basically abusing the data structures used by the heap, actually the linked list, to overwrite pointers or overwrite arbitrary memory. And the first example is frontlink. Has anyone here ever heard of frontlink? No? Anyone is awake? Okay, great. So frontlink was actually the first or the second heap exploitation technique ever published. It was published in 2001 in a paper called Voodoo Malloc Tricks. The idea goes like this. Let's look at list insertions, right? When freeing a chunk, we're inserting into a list. And this is a code, it's a very simple code for list insertion. You're inserting P right after the prev node, the prev link. And if you control this prev chunk FD, the pointer FD, you basically have a write pointer to what where. Write P is a chunk you're inserting into the free list, so it points to user data. It was just freed, it just held user data. And since the attacker controls the FD, because they have users to free or buffer overflow, they can just write this pointer wherever they want, which is nice. But controlling prev is not so easy. What is this prev? So this prev, when it's a small bin or fast bin or whatever, this prev is it's the head of the list. And the head of the list is not a chunk. The head of the list is in the main arena. So it's in this GLibC data section. However, there is a very nice blog explaining how you can actually override the list head with some primitives. I recommend reading. And my most favorite way is insertion into the large bin, because large bin is sorted, so the previous can be a chunk that is used after. You do a use after free and actually overwrite this chunk or overflow into this chunk. So if you free a big chunk, it will just be inserted into this large bin in the right place. We'll see an example in a second. This thing was not mitigated. If you open many heap exploitation papers, they will start with, in 2001, there was the voodoo Malloc tricks, blah, 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 and it was mitigated in 2004. No, it was not mitigated. That's for sure. So check me out on that. So if you want to read articles about it, there is an upcoming POC GTFO in June. So there is a paper, an article I wrote called House of Fun, which explains this in many details. And there is also the original voodoo Malloc tricks you may read. These are the two articles that you can read, or you will be able to read soon. And let's go to an example. So again, we start with our empty heap. And you can see here the large bin of 400 to 430, and it's empty, so you see it points to itself. This time I only illustrated the back pointers, but again, it's doubly linked circular list. And here you can see it's empty, and we make an allocation of P0 of size 400. And it's an allocation, we break the top, we have a nice allocation. We make another small allocation just so things won't merge when we're freeing them. So the second chunk is also used, but we're not assigning it to any variable. And we make a third allocation of size 420, which is bigger. And it's right after that, we assign it to P1, and we allocate another separator chunk of the size of 20, so things won't merge. And now to my first trick, we're freeing this chunk of 400, and we make a big allocation and free just for it, so it will move from the unsorted bin into the large bin. Remember, when we free chunks, they're moving into the unsorted bin, and to move them to the large bins to sort them, you need to make a big allocation or something that cannot be served. So the system would actually sort the chunk and put it in the large bin. So this is what we're doing, freeing the chunk, making a big allocation so it moves into the large bin. And you can see it in the linked list of the large bins. And next, we're using our vulnerability, and we are overwriting this back pointer to dead beef. So now it points to dead beef. This was a use of a vulnerability, any vulnerability that can do it. And what we do next is we're freeing P1, and P1 is 420 hexabytes, so it goes to the same bin, but since the bin is a sorted list, it would be inserted after, or before, depends how you look at the pointers, this chunk. So when freeing it, in order to insert it into the list, the system would write that beef pointer back to P1. So basically you can write P1 or the address of this chunk wherever you want. In this case, we want to write it to dead beef. Now, usually dead beef is not allocated, is not mapped, so the whole thing would crash. However, if it was a bit annoying. So if dead beef is mapped, you would just write a pointer to this chunk to dead beef. And this is how the front link method works with large bins. Okay, the second method, also described in the same paper, Voodoo Malloc Tricks, is called Unlink. I think you're more familiar with Unlink, right? Who's heard of Unlink before? Yeah, quite more hands. Okay, great. So, same paper. The idea is the opposite. Let's look at when removing a link from the list. So this is how you unlink. You have actually, it's doubling, so you need to do both sides, but this is what you do. And a user that controls the back and the forward actually gets a write what where, right? If you control the back, you control where to write. And if you control the forward, you control what to write. So you get a write what where. And this was mitigated in 2004 when the paper is saying there were mitigations, a series of patches mitigating some existing attacks. This is what they mitigated. And so they're actually checking that the back forward points to the chunk you're unlinking from the list. And if it's not, it calls the print error function. This attack is still useful. Unsorted bin attack is basically an unmitigated unlink. It sticks to this day. And there is an attack called House of Cards that was outlined in a blog post by Tcache, which is a very nice read. The entire series of blog posts is a nice read. And what he was suggesting is overwriting the check action global variable. When it's zeroed or when the least significant bit is zeroed, then the print error function does nothing. It's a no-op. And then you can unlink again and do whatever you want. And also, if you unlink a pointer to attacker control data, you can override this pointer in various ways. So that's also a nice way to use the unlink, even with this mitigation. The second category of attacks is the functionality attacks. So the thing is that the allocator is an allocator. It allocates data, which the user then writes. The user is an attacker in our case. So if you can trick the allocator to allocate memory in regions it was not supposed to allocate, not in the heap, in the stack, in the globals, you can just write there, and this is how you get to write your data wherever you want in the process memory. So the first attack I'm going to talk about is the Tcache poison attack. Again, Tcache was introduced in 2.26, so it's quite recent. And this is the Tcache code. As you can see, there is no verification of nothing here, but an attacker that controls this next pointer or the FD pointer, because it was a patch, they're not using the same data structures, or I don't know why they're not doing it, but for some reason. But attacker that controls this next pointer, which coincides with user data, in a use after free situation, for example, can just poison the cache and put whatever pointer they want in the cache. And in the next allocation, Malloc will return attack and controlled memory location. So let's see an example. Again, in this case, we have a buffer on the stack, and it's size of 8 bytes, whatever, and we make a first allocation of size 90, for example. And then we're freeing this allocation, so it goes into the Tcache. You can see Tcache is an array of pointers to linked lists, and you see the list contain only one chunk, the chunk we just freed, and this chunk points to null because the list ends. And then we're using our use after free vulnerability or the buffer overflow vulnerability, doesn't matter, to point to this buffer on the stack. Now we make an allocation. The allocation returns this chunk, the corrupted chunk. It's not of our interest, but the more important thing that this allocation does is moving the buffer on the stack into the Tcache, into the cache, and this would be the next allocation. So next allocation actually allocates this buffer on the stack from Malloc. And now if we can write to it, for example, we can write dead beef in little endian. We're just writing to a buffer on the stack. That's a very nice attack. Other functionality attacks is all the attacks from Malloc Maleficarum and other stuff similar to it. So just links, I cannot talk about them. They're really complicated, they're really nice. Malloc Maleficarum is a classic article from 2005, and still to this day, many of the attacks in this paper are relevant. So, and it's a fine read. Okay, so the last category is the restricted functionality attacks, in which you have a more restricted vulnerabilities. You cannot write any kind of data you want. You can only write to 1 byte of data. You can only write null bytes, stuff like that. But you still want to trick the allocator, and you want to overwrite other data that is in the heap. So do you have some data on the heap adjacent to your vulnerable chunk, and this is what you want to hit. This is the chunk you want to corrupt. And in this category, there are 2 papers that I know, for more than 2 papers, but two techniques. The first one is the poison null byte that was published by Google's Project Zero in 2014 or 15, I don't remember currently, in which they demonstrated how overflowing even 1 null byte into a chunk can result in interesting overlapping chunks or chunks that are removed and forgotten from the heap. And there's also my paper from the one before previous POC GTFO. I called it fragment and write technique, that you can turn relative overflow into a you can convert a linear overflow into a relative write. So you can read these two papers. There are other cool tricks that I cannot put in any category in my head, but I still remember them, and you should probably know about them. So it's the unmap any page, also from the series of posts by Tcache, that basically an attack that lets you unmap pages, and it's really interesting to combine it with the stack, because an not mapped page in the stack that is hit is actually immediately mapped by the system and zeroed out. So you can zero pages on the stack, which is nice. And also this allocation of the bins, you can actually allocate over the heads of the list in the bins in the main arena. Yeah, and that's for the attacks. Now, flow hijacking. I mean, we've written our data, we know where things are. How do we hijack the flow? How do we control PC? And for this matter, we have, this is the become a wizard part. And my favorite is using the Malloc hooks. So there are hooks in the GLibC Malloc. Here is, you can see the function of Malloc internally. This is how it's implemented. And the very first lines, what they're doing is reading a global variable called Malloc hook and checking if it's null or not. If it's not null, it will just jump to whatever is pointed there. So if you can override this global variable, which is in GLibC, you can get code execution. It's similar in free and in realloc and in the other API calls. So you have the free hook and the realloc hook, and you can override them. Yeah, and what's really nice is that our assumption here is the user can invoke some API functions, right? This is how we're doing all our exploits. So it's really straightforward. The user can already invoke these functions. So when overriding the hooks, it just invokes the exploit chain. And less known fact is that it can also be reached from the IO system. So a very big printf, for example, would allocate a buffer using Malloc to hold the information you're writing. So you're doing IO with. And if you, so it's over 2K, over 4K, I don't remember exactly. And if you really have a really big printing, it will be even double. So it'd be realloced and realloced again, and eventually freed. So it can be nice in situations you can only write 1 byte at a time. So you're writing 1 byte at a time of realloc, and then you make a really huge print. You're using only malloc and free to write 1 byte at a time to write the realloc hook. And then you're invoking realloc, and the hook is ready, right? All bytes are written. You cannot do it with the malloc hook because you write only 1 byte at a time. So the next time you'll call malloc, you will screw things over. But if you're doing it with the realloc and printf, you're getting everything neatly done. You can see an example in the Baby Heap 2017 challenge. Yeah, it was quite cool. And many other. So the next one is the one I really like. I think I never seen it except in one of my exploits and in Mac from Dragon Sector exploit. It's the DL open hook. So there is another global variable called DL open, which points to a table of functions, specifically the DL open mode. And it's called whenever you're doing DL open, whenever you open an external library. And attacker can very easily trigger it because it happens when there is a detectable error. So if you remember the malloc print error function, this function at some points tries to print a backtrace, and to print a backtrace, it's using a function in a different library, and they're actually doing DL open. The GLibC does DL open to get this function. So you're triggering a very detectable error because you can write some stuff, you make some inconsistencies, and it will just do DL open and use the DL open hook. It's very naturally combined with the frontlink attack, because if you remember the frontlink attack, it grants you a write pointer to user data where. And this is exactly what you want. You want to write a pointer to a table of functions. So you cannot do it with the hooks. The hooks should point immediately to code, right? We have the NX bit. Code is not writable, but you can do it with a virtual table, and DL open hook is a very nice mechanism to do it. If you want to read a write-up, so it also will be part of my upcoming POC GTFO write-up. And next there is the GLibC file struct. This is known as part of the House of Orange. There is this global variable also called IO list all, which is a linked list of open files. And when on process termination, it invoke some of the functions, for example, the overflow function from virtual table. And attacker can also trigger it quite easily, similar to the DL open hook detectable error, then the print error function, process termination, and so on. It was partially mitigated with a function called IOValidate vtable, which checks the vtable pointer points to a section designated only for virtual tables, but it's not enough because there are plenty of functions there and you can bypass it quite easily. So you can read the original House of Orange write-up if you want to see how it was in GLibC 2.23, and in GLibC 2.24 with the mitigation. You can see the mitigation bypass. It's the 300 challenge from the last CCC. So yeah, one thing that in this, I don't know when it was released, but in the last version of GLibC Malloc 2.27, there is a mitigation to print error, and it just calls abort. It doesn't print backtrace, it doesn't flush the files, nothing. So yeah, so all the process termination hooks we were talking about, the DL open, the file struct, are not relevant in this last version, so it complicates exploitation. Maybe we need to find other paths to trigger these hooks, but the hooks are still there, just not the way to trigger them. Yeah, and last thing is the program-specific thing, right? You can overwrite return addresses, you can overwrite vtables, you can overwrite function pointers, all the things we love. So yeah, here's the bonus, the setup. This is how I approach CTFs, and this is code. So I'll demonstrate with the 300 challenge from the last CCC. And many times when you have your victim program, it's not the same version as the libc installed on your laptop. So you can use the LD preload hook to actually load the different version. Here you can see I'm using the Pwn library, which is awesome, and thanks to the people who wrote it. And you see I'm loading a different libc to the 300 binary. This is the 300 challenge. This is how I started, using the LD preload hook. If you don't have the libc, you don't know which libc is used, you can use this website. It's a libc database, which you give the least significant bits of some symbols you know, and it gives you a list of possible version of libcs. And sometimes the libc and the loader are interdependent and don't play nice with each other, and then you really have to set up a VM, or maybe someone has a better solution, not me. So yeah, next, well, when you're trying to exploit GLibC Malloc, you have the libc, and you want to debug it, so you want to have symbols. And many times, I mean, nobody compiles their own libc. We're using Linux distributions, and let's say we're using libc from distribution Ubuntu 17.10. So the distributions has symbols, right? You can just download the packages of symbols and unpack them and load them into your GDB. So this is how you load them into GDB. There is an add symbol file command. However, there is an annoying bug in this command. So this is my code to actually explicitly tell GDB for every section where the symbols are. You can just copy this code, and you see in the last line, I'm attaching to the debugger and giving it the command to load the symbol file. And sources is very similar. libc is part of a distribution, say 1710, and distributions have their source files also packed nicely, and you can just download it. So this is the example for 1710. This is the source code. And you can load it to your GDB with the substitute path command, which tells GDB where to look for the original source code. And if you want to know where it is currently looking, so you can do the substitute path command correctly, you can use the info source command to find where it is currently looking. So that's putting it all together. You can just copy it from my GitHub of the presentation. This is it. Quite nice. That's it. Time for questions. If you want to contact me, in the end of the presentation, there are like lots of references to read. And yeah, any questions? Wow. No one. Do you want me to put the link to the, let's put the link again, so you can, let's make it like this. Oops, yeah. Yes, the guy over there.
Thank you very much. Did you try to attack any other libc, UC libc, muscle, or the Windows libc?
No, they're quite different. They're actually very different. Windows currently have these cookies, right? That you really need to check the integrity of all pointers when you're inserting and removing from the list. So I don't know if any attacks against the heap directly would work. You can only do like the normal use after freeze that you hope to get the chunk that is still in use and overwrite its data. But directly against the heap implementation itself, I'm not sure it would be as easy. Yes.
Thank you for your talk. I'd like to know how stable is the libc implementation, so the data structures and algorithms. Does they change on a frequent basis? Or?
So they don't change very frequently. The picture that I showed was from GLibC, I think, version 3 or something like that. They add different optimizations like Tcache that was recently added, or the large bins that are now they're like kind of doubly linked in a skip list way. So it was an improvement, but the basic data structures remained as they were since 2001. Okay, the attack from 2001 still works. In the upcoming article, I will release a POC that can work against all versions of GLibC. The same code works on all of them. It's quite simple code, actually. 32-bit, 64-bit, whether it's GLibC version 2.3 or 2.27, they all work. So they're quite stable. Okay.
We still have 15 minutes.
Oh, okay. Do you want me to dance or? Yeah, it was. I thought I don't have too much time, and now I see I have more than I expected. So yeah, any other questions not related to this talk specifically? Yeah, you can follow the link. Like press escape, you'll get nice overview of the presentation. Oops. So you can just go to the last slide, open it, and you can, why doesn't it work? So, and then you get Markdown, so you can read. Let's see, it's a bit slow, but okay, so you can just, for example, go to the attacks chapter, and you can read everything in Markdown. You don't have to actually render the presentation. So this is why I hope it would serve as a reference, because it's really easy to read. And this was actually hard work to make it both Markdown and a presentation. And I know the presentation itself is not perfect, but then you can read it as Markdown as well. So it was one of the things I really wanted to happen in using this platform. And let's go.
Okay, so if we don't have any more questions, we can stop here.
Oh, wait, there is a... What a surprise.
Where?
So those tricks are very useful for CTF, but do you have an idea how frequent it's useful in real programs? But because I feel like there's more just heap overflow or easy overflow of objects in real exploits. But do you use those tricks in real programs?
So a year ago, I found a vulnerability, just the buffer overflow in VLC, when they're rendering the, not in the rendering, but in parsing the subtitles. So they parsed the subtitles and they had a very stupid buffer overflow, but I could not write null bytes. So this is how I got into GLibC Malloc in the first place. I wasn't intending to, but this was the vulnerability. So it exists. I believe there are more these kind of vulnerabilities in VLC specifically, and they just started a bug bounty. So I recommend looking at it. And yeah, there were vulnerabilities in sudo application, so it was quite common in real life. So yeah, I mean, I recommend everyone move to Rust or something, you know, some memory safe language, but it's still common enough. Yeah, over there.
So you said you are not going to investigate for LFH, but do you have any plan for doing research for galloc, talloc, for other like used in Firefox? So are you planning to do some research on it, or just GLib?
So I think it depends on the vulnerabilities I will be looking for in the future. I'm a vulnerability researcher, so it depends on what I would find. I'm driven by, I wouldn't say by chance, but by work mostly. So the VLC is how I started with GLibC Malloc, and if I find vulnerability in that would happen to be in the other implementations, I would look at them, but not. I don't have any concrete plans on researching them. But I do gonna play the CTF tomorrow, I hope, or in 2 days. I hope so. If there will be vulnerabilities in Malloc that I would need to exploit, I'll start reading about it.
Okay, so
yeah.
I think we can stop here.
Okay, thank you very much.
We can have lunch.